Welcome back. Today's Gauss's Law. It is one of the most powerful and elegant results in electrostatics, and today we'll understand what it means, how it works, and what makes it special. By now, we understand that electric fields extend outwards from charges, and we can represent them using field lines. But wouldn't it be amazing if we could find the electric field due to a charge distribution without complicated vector math? That's exactly what Gauss's law allows us to do. Let's begin with the statement. Gauss's law states, the total electric flux through a closed surface is equal to 1 upon epsilon naught times the total electric charge enclosed by that surface. Mathematically, phi e equals closed surface integral of E dot dA equals Q enclosed divided by epsilon naught. Here, E vector is the electric field at a point on the surface. That means it tells us the strength and direction of the electric force at that location. dA vector is a small area element on the surface. It is a tiny portion of the surface with a direction perpendicular to the surface at that point. The circle on the integral sign means we are taking the integral over a closed surface. Examples of closed surfaces are a sphere, a cylinder, or any shape that completely encloses space. Q enclosed refers to the total electric charge present inside the closed surface. It doesn't matter how the charge is distributed, only the total inside the surface counts. Epsilon naught is called the permittivity of free space. Its value is approximately 8.85 into 10 raised to the power minus 12 coulombs squared per Newton meter squared. So what does this really mean? Imagine wrapping an invisible bubble around any charge or group of charges. This is your Gaussian surface. Gauss's law tells us this. The number of electric field lines leaving the bubble depends only on the total charge enclosed inside, not on the size or shape of the bubble. If you double the size of the surface, the flux remains the same. If you make it into a cube instead of a sphere, still the same. Only the amount of charge inside matters, not the charge outside and not the geometry. Let's derive Gauss's law for a simple case. A single point charge, denoted as Q, placed at the center of a spherical surface of radius r. According to Coulomb's law, the electric field at every point on the sphere is given by E equals 1 divided by 4 pi epsilon naught multiplied by Q divided by r squared, where E is the electric field, Q is the charge at the center, r is the radius of the spherical surface, epsilon naught is the permittivity of free space. With a value of approximately 8.85 into 10 to the power minus 12 coulombs squared per Newton meter squared. Now consider a small area element dA vector on the surface. This vector is radial, meaning it points directly outward, just like the electric field. So, when we take the dot product of the electric field and the area vector, we get E vector dot dA vector equals E multiplied by dA. Since both vectors point in the same direction, the angle between them is 0, and the cosine of 0 is 1. Now, we add up or integrate over the entire surface of the sphere. Total flux equals closed surface integral of E dot dA, which equals E multiplied by total surface area. The surface area of a sphere is 4 pi r squared, so total flux equals E multiplied by 4 pi r squared. Now substitute the value of E from Coulomb's law. Phi E equals 1 divided by 4 pi epsilon naught multiplied by Q divided by r squared multiplied by 4 pi r squared. The r squared in the denominator cancels with r squared in the numerator. 4 pi cancels with 4 pi, so you're left with phi E equals Q divided by epsilon naught. This is exactly the statement of Gauss's law. So we've confirmed that for a point charge placed at the center of a spherical surface, the total electric flux through the surface is equal to Q divided by epsilon naught, the total enclosed charge divided by the permittivity of free space. Now here's something important. Although Gauss's law is always true, it's not always useful for calculating electric fields. To apply it effectively, certain symmetries are needed. These include spherical symmetry, e.g., point charges or uniformly charged spheres; cylindrical symmetry, e.g., long charged wires; planar symmetry, e.g., large charged sheets; In such symmetric cases, the electric field is either constant in direction or magnitude, or both, over the surface, allowing the integral to simplify. So, remember, Gauss's law is most practically useful when there's geometric symmetry. A quick note, Gauss's law does not tell you the electric field at a specific point due to charges outside the surface, the distribution of charges on the surface of a conductor, the value of field without sufficient symmetry. It only relates net flux to net enclosed charge. Let's recap what we've learned. Gauss's law connects electric flux through a closed surface with the total enclosed charge. It is mathematically phi E equals closed surface integral of E dot dA equals Q enclosed divided by epsilon naught. It works best when applied to highly symmetric charge distributions. It simplifies electric field calculations for spheres, cylinders, and planes. It's a universal law, always true, but not always easily usable.